So yeah. So thanks everyone for showing up. Oops. Pull up. So start out. Just so everyone knows, this is the building machine learning model open source using Python. I'm Jim Schwabel, the CEO of Neuralex Labs. Our vision at Neuralex is to make voice computing accessible to everyone. One element of that is kind of doing workshops like these and teaching, how do you build a machine learning model to the community. We built a team of about 15 people over the last 2 years and have built a portfolio of technologies around voice devices and voice software. The first product we built in our company is called Surveylex, which is the world's first voice survey platform, and I'll get into that a little later. This workshop was inspired by a book that I wrote called Introduction to Voice Computing in Python. Over the years, I've been mentoring a lot of fellows in our lab. We've had about 40 research fellows, mostly at the University of Washington, but all across the world. And a lot of them have done demo projects, and they've come to me and said, how do I featureize voice files? How do I model voice files? And so I thought that it was really efficient to write this book. I'll have some books after if you guys want a copy, and just come up to me and we can figure it out. But I thought this was a more scalable way to scale this knowledge beyond workshops like these. So I'm going to skip to starting out. What is voice computing? So I think this is one of the first things I wanted to start out in this workshop. When I looked at voice computing's definition, there wasn't even a Wikipedia article written about it when I started writing my book. And so I was really curious, how is it defined? Most people define it in terms of Alexa voice assistants. One of the first things I wanted to say is, in my perspective, I don't believe voice computing is equivalent to speech recognition or ASR or voice assistance for that matter. And this is what I found when I searched Google when I first started writing my book. It's a lot broader than that. It includes things like natural language processing. After you transcribe a file, what are some features in the syntax and semantics of that beyond speech recognition. But also in data science, how do you model speech and text data? How do you visualize audio files? I think this is a really hard problem. How do you play back audio? How do you record audio appropriately? What are some protocols for collecting audio? I think that's a big area of innovation we've really standardized. What are some codecs out there? How do you encrypt audio files? How do you process audio files? How do you even package server architectures for large-scale distributed computing and audio? So this definition of voice computing makes it really flexible to focus content not only in this book, but also gives you a perspective of where this workshop fits. And so when I look back and thought about how do I define voice computing, I thought the simplest and easiest definition is just being the discipline that develops hardware or software to process voice inputs. I thought in focusing on voice as the input, it makes the definition a lot more flexible, and it extends to many other things like how do you read-write audio files? How do you record voice files? How do you clean stuff and all the other things I was mentioning? It also includes a whole thing in hardware where if you need to create your own custom hardware to reach a certain level of audio fidelity, say you want an 8-array of microphone to capture certain voices in a room and say, hey, at certain times you want to focus on this side of the room versus that side of the room, how would you design a voice computer to do that? So it makes it a lot more flexible to think beyond the hardware limitations we have and say voice assistants to make your own embedded voice computers, potentially very intelligent voice computers. And so this workshop focuses on machine learning aspect of this book. And I really want to take you through how do you go from start to finish and not only building a machine learning model, but thinking about the data sets out there that we can use, how do you featureize audio, and how do you model audio. So the first step, in my view, is like, how do you engineer a data set? I think as a data scientist, you always think, what is out there already to start with, and where should you build a new data set? So one of the things to consider before we talk about data sets are all the biases in data sets. Your voice changes with your age. So the spectral power is a known feature that in children and in frequency, obviously, child versus adult, the children have higher pitched voices than adults. Also, the power of your voice as you age, your power actually becomes a lot less as you become an elderly patient. and in children have lower power voices, and it normalizes in adulthood. The type of microphone you use is very important. So a iPhone is not equivalent to, say, this laptop, and this laptop isn't equivalent to some old recording instrument. So when you think about data sets, you should think about what microphone was used and was it controlled for, because that can throw off a lot of your models. Gender is obviously male, female. That's one of the most obvious confounds of noise. Are you inside or outside? Is there a car going on in the background in a few sections of your data set? Is it a very clean sample indoors? Time of day is one that is often overlooked as well. In the morning when you wake up, you have a deeper voice. So that's something to think about. If your fundamental frequency is really deep in the morning and then it linearly increases throughout the day, it might throw off some of your models, and wondering why is like all the models working at 9 a.m. but not say in the middle of the day. And then the last thing, accent and language. Obviously, if you're building a model for an American accent, it might not work in, say, a Chinese accent. And there's elements of prosody that might not transfer across regions and cultures. Other things to think about when you're choosing a data set and thinking about engineering a data set are things like licensing rights. Is it open source or for research use? Whether or not how do you label this data? So a lot of people, experts, manually annotate this data, or you can get clinical labels in the case of, say, building a model for, say, depression that are done by a trained psychotherapist or a psychiatrist. You also can look for audio quality issues with compression. This is a common problem. If you collect data through a cell network, you've compressed audio. If you collect it through WebRTC, it's high quality. And then recording lengths. So I often build a model. It works fine on a 20-second sample of audio, but then when you get a 1 second or a 5-second sample of audio, you don't normalize things appropriately. It throws things off. So I want to start out just kind of thinking about these things. I also just, during this talk, for the developers in the room, open sourced a list of all open source data sets and voice that I think would be useful to you. I just want to be of value. So it's a very big list of all the speech data sets here. There's like an audio MNIST data set. I love to use the common voice data set. It's the largest data set I think that is used for things like accent detection or ASR, automatic speech recognition. And there's also things like Parkinson's disease open source data sets. And the one that I'm going to use later is Vox Celeb. There's 5,000 unique speakers in this data set. It's the largest open source data set for voice. It's taken off YouTube, and there's a great research paper on it. So check out these data sets later after this talk if you guys want to get into this field. I often think it's great to start with an existing data set if you're just starting to learn the program. The other thing too is if you need to engineer your own data set, we have built our own product to do this. You can create and design a voice survey and curate your own labeled data sets with SurveyLex. I'm going to skip the demo here because I'm not trying to sell you on our product. But there's something that we built internally because we commonly face the problem of we needed, say, 100,000 patient trial data on, say, health trait data with health symptoms and just creating a normative data set. And so doing it with SurveyLex was easier than using open data sets because none of them were out there for that purpose. So let's start out with featurization techniques. So in the book we wrote, this is chapter 3. You can check it out if you guys want to look deeper. So I guess how many people in the room are developers? Say half. Non-developers. I guess okay. So I'd say half and half. So I'm just going to cover this quickly because I know for developers you know what featurization is. But I like to equate features kind of like fingerprints. You also can define it in many ways, but I like to use this example. So if you have a human face, like what elements would you say are features on the face? Well, you have eyes, you have a mouth, you have a nose, you have hair. A lot of these are hard cascades. But the idea of taking a feature is from these elements, you could classify, say, a human face from something else. And so a lot of things, feature selection is how do you compress information to a lower number of dimensions, say all the pixels in this image, to just a few different elements like eyes, face, a nose, such things that you can differentiate, say, a human face from a non-human face. In the case of audio, some of the really interesting features that I'm interested in are features that differentiate diseases from non-diseases. So things like depression, you might think of a depressed person versus a non-depressed person as having a slower rate of speech, probably a duller tone, and shorter sentences. So those will be elements in a feature of a session that, say, in the same person might be a more depressed state versus, say, a non-depressed state. In the case of Alzheimer's, features are like things like pause length. So as you age and you have a memory impairment, the pauses are a good feature to differentiate whether or not you have a cognitively impaired group versus non-cognitively impaired group. And so the idea of feature selection and features is just trying to take a more compressed representation of an element. In the case of audio, kind of being intelligent about thinking, what are the features of a thing that lead to a good way to differentiate the groups. In Python, a lot of the ways that I guess you represent features or work with data is with NumPy. It's just a really easy way to create arrays, create features. I have some of these here, which are pretty obvious, but you can index arrays, kind of look through data, serialize it to JSON. This is kind of, I'm going through it quickly because I know a lot of people are developers here. Get the shape of an array. So for example, you might have just a big array of features of, say, audio MFCC coefficients, and you want to get the shape and look at the size. Do things like get means, standard deviations, mins, maxes of arrays, create zero arrays. So a lot of these things you do to represent, say, audio files. And in the case of audio, the main types of features here we define in our lab are audio features, mixed features, as I'll get to, audio features, text features, mixed features, and meta features. So the first one, audio features, we look at as features that are representative within the waveform. So if it's from a wave file, we consider that an audio feature. So we represent it by data type as opposed to, say, prosody that might have a mixture of features. It's just audio feature would be if you have a wave file and you get some feature from the wave file itself, it's an audio feature. There are things like MFCC coefficients, which are used for automatic speech recognition, for differentiating phonemes from each other. MFCC deltas. The fundamental frequency is often used for things like gender detection, jitter, shimmer, formant frequencies, file duration, root mean squared energy. There's a lot of them here. There's a lot of libraries to get features. In the GitHub that we have in the voice book, we actually show all these features and show the representative use cases for each of them that has a good representation, so you can get a good intuition as to what these features mean. I also have a lot of things in the GitHub for featureizing things. I can kind of pull it up really fast. This is more of a workshop. So if you go to GitHub and see the repo, go here. Oh, here it is. See this repo, you'll see featureization chapter, and there's a whole list of different featureization techniques. The first one here is Labrosa featureize. This library, Labrosa, is actually a really great library. If you guys haven't worked in speech processing with Python, this is probably the best library to start with. It's very well documented. They have all sorts of feature representations that you can easily extract. You can get onset detection, all these things direct from the library. So check out their documentation. But I do have a very simple implemented script that extracts all of the features from Labrosa that we use internally. And also you can quickly format it in the terms of features and labels so that you know what the represented feature arrays are in terms of the labels. So you'll find that in a lot of these scripts that I have, it's just easy to see the features and labels so that you get an idea of what these features are, which is a common problem. So yeah, so there's Labrosa. There's also a library out there called Pi Audio Analysis. If you guys haven't seen it, I want to just show you. I think this would be, yeah, so Pi Audio Analysis. This was another great Python library I would highly recommend. They have a wiki here. Oops, no. This is mine. So my repos. Let's go back to GitHub. I don't know why I did that. Yeah, so this was published by a dude from Greece, it's just a great place to start as well. It has a greatly documented wiki with feature extraction scripts of a lot of these features: zero crossing rate, energy, entropy of energy, spectral flux, MFCCs, chroma vectors, etc. Highly recommend Iota analysis, mostly because it's well documented. It's a really great beginner library for modeling as well, if you guys want to get features and model. Another thing is a command line featureization technique with SOX. So SOX is sound exchange. I have a script I wrote in the voice book for SOX as well. You guys might have heard of it for a lot of the command line things, but I actually had taken the standard output of some of these features of things like the length, the maximum amplitude, midline amplitude, and others. What I like about SOX is that it's a C library and it executes really quickly. So you can featureize things a lot faster with SOX to get a first pass with features if you use a huge data set. So it's how I tend to use it. And then I'll get back to the library. But yeah, so that's some of the, and then there's AudioSet. So I highly recommend you guys see AudioSet. AudioSet is a data set released by Google. They created 632 audio events with over 2 million annotated 10-second clips. Really great data set for object detection. They created an embedding called AudioSet that did dimensionality reduction, have 1 second intervals where you can get feature arrays of mostly MFCCs and things, but it's really good for object detection and research. So if you ever need to use something for object detection, I highly recommend AudioSet. And I also have in my book here an AudioSet feature script that you can quickly use to do that. It will download the model from Google and repackage it to quickly featureize things in this format as JSON. So first step, figure out feature arrays. I wanted to just give you guys something useful to kind of reference later if you guys want to delve deep yourselves. The other type of features we think about when we model voice files are text features. So text features to us are any type of feature that results in the transcript of an audio session or a voice session. So like you might ask someone, how's your day today? And you're trying to detect depression. Well, it's all the strings from the transcript there. So you can think about the transcription method here matters. If you use a Bing transcriber versus a Google transcriber versus Pocket Sphinx, which is an open source transcription engine, it's really important to keep that constant because that might throw off some of the models you build. But with that in mind, let's delve deep into that. So the 4 libraries I tend to look at for featureizing text is any NLP problem: Spacey, NLTK, GenSim, Stanford NLP. In the case of speech things, I count usually character frequencies a little more here because the phoneme models sometimes are representative in the text. So I have character frequencies as something that I usually count, and they can be important in some scenarios. And like things like named entity recognition, sentiment, and things like that are in these libraries. So I'm not going to keep pulling up my GitHub because I feel like that's probably annoying you guys. But I do have a script to featureize things with NLTK. It has a lot of these features and labels as well. Spacey, I really recommend Spacey for production grade use cases. It's a lot faster featureizer, and it's well documented. And GenSim. And then mixed features are a little more less intuitive. I like to think of them as ratios between, say, an audio feature and a text feature. You might want to know like the spectral power of the word "the" like at the first second and see if that's representative or important for a classification problem for like depression. So looking at time series elements and seeing like what are some ratios of power to say the word "the," that's kind of interesting. So some of these things I like to randomize and just see like what is working with a mixed feature in a modeling problem. So I have some scripts here to, for example, randomize some mixed features given all the other feature arrays that I showed. And then meta features. So meta features I like to define as features that are from machine learning models. So you might know somebody's age, gender, microphone, et cetera, from models you run, and they can be used kind of to feed into a machine learning model to train it. So you can correct for these things. And so in the book, I have a lot of machine learning models open sourced, things like emotions, audio quality, fatigue, stress, speaking type, is it normal speech or abnormal speech, accents, ethnicity, things like this. So some of these things usually can correct for some of these biases I mentioned earlier. So if you use some of the meta features, it's often good to say, hey, like if it's in a neural network or in a regular classifier, it's good to correct for them. And that's what the output looks like in using some of the featureizers we have in the book. And then, in audio, common problems, dimensionality reduction, MFCCs are usually taken over 20 millisecond windows. So when you have, say, a minute long of audio, you often want to compress that into smaller size. And so there's a lot of dimensionality reduction techniques that are open sourced here that I put in the book to make it easy to kind of select one. I think that you guys can look at that later, and feature selection techniques. So how do you select a feature that's most relevant? A lot of these things like recursive feature elimination or anything else are represented here. And these are kind of a lot easier to say, like, how do I do this on Google? And you usually find such tutorials. So I don't know if that's super useful. So now let's get into modeling. So I guess we're 20 minutes in, so kind of on schedule. So let's get into modeling. So with machine learning modeling, again, I like to make the analogy to lightning. Like I feel like machine learning for the first time is kind of, I like to say, like the time we saw lightning for the first time as humans. You might be in awe of it, you might be scared of it, or you might know how to use it and harness it, and you're going to be curious to study it. And so I think everyone in here is hopefully of the curious type and wants to learn about it. And we'll go a little deeper into it. So what is machine learning? Well, there's really two main types of machine learning problems. Classification problems, where you're trying to output a class from a known set of training data, or regression problems, where you're trying to output a number like in between 0 and 1, usually, say as a representation, with training and testing data. And so I think the way to think about this is like if you're trying to output something like a class, like male, female, usually going to feed in some data, and you test it with some data. And there's really two main types of learning, supervised learning and unsupervised learning. So in supervised learning, you use a training set, say like Apple, where you're trying to say, okay, given a group of apples of training set, and you see a new apple, well, if you have some known representation from those apples, you can say it's an apple. Whereas if you say unsupervised learning would be more like if you have a cluster of things, how do I cluster them into things? So you might not know it's an apple, or in this case, looks like almost like a watermelon. Or avocado. Like how would you tell like the different sets of classes from any learning? So you don't know what they are. You just know there are 3 segments. And so for most use cases in speech, I would say I usually typically do supervised learning on things like depression detection and things like that. So that's what I'm going to probably go over later. And then, like I said, you probably want to get some training data. For this demo, I was going to use the Vox Celeb dataset and classify gender, because I felt like that would be a very simple way to show you guys. Labeling this data. So one of the problems in machine learning is labeling. I think they annotated it manually in their lab with a lot of research assistants. It took a really long time, kind of like the ImageNet dataset. And so I'm just going to go through this quickly. So yeah, the one thing to know with a classification and regression, in the book I have a lot of training scripts like this that will take in a lot of folders of files, like audio files, and it will run a lot of models like AdaBoost, gradient boost, logistic regression, hard voting, k-nearest neighbors, and pick the best model from the group of models so that you can kind of see quickly which model type or model family is working. This is often useful because in speech, some of the problems aren't as clear as, say, knowing, say, a naive Bayes would work versus another just from intuition. So I find oftentimes it's good to start with this and kind of look deeper and optimize a model. And so that's one thing I feel like and I'll use that in our demo in a little bit, show you how we do that. And then it makes it really easy to load models into production as well. Another thing we have in the book are a lot of regression models. So we have a very similar approach, minimizing the mean absolute error in a lot of techniques like linear regression, ridge regression, lasso. So coming from an engineering background, I just kind of listed them all out here so you can see which model is working and pick your model appropriately. And so this makes it easier. It kind of saves you a little time because scikit-learn, sklearn documentation is pretty clear, but maybe save you a little bit of time starting out with one of these scripts. And then one thing I go over in the book is AutoML techniques. So for speech, I really like this library called TPOT. Some of you guys might have not seen it. So for everyone who doesn't know what AutoML is, it's the idea of just taking data, putting it through our features, usually putting it through some engine, and it auto optimizes models for you. In the case of TPOT, they use Bayesian optimization, and they do recursive feature elimination for you automatically. So you do all your raw data collection and data cleaning, and TPOT itself optimizes all the parameters for you. So I really like this because this is the most manual process in building a machine learning model. You can build a model, but how do you optimize it? I think TPOT does a great job with doing it in a stable way. And so I made it really easy to actually, in the book, just run a train audio TPOT script with 2 folders of audio files and then output a classifier. Whereas before, the TPOT itself, you'd have to run a separate script. So it saved a few steps as well. So same with regression. TPOT has a good regression score. I think it's mean absolute error it uses here, but it minimizes that in the Bayesian optimization, and you get a good model for production. So I really highly recommend it. I've been using it actually for the past year in a lot of problems, and it does a great job to get a good result. And then some larger projects that some are open source, some aren't open source. I've looked into Devol, which is a similar Bayesian optimization, this is evolutionary algorithm. It uses an evolutionary algorithm to select a Keras neural network and optimize a neural network to a given problem. The problem is with a lot of these AutoML techniques is they're computationally expensive, they take a while, but you can still do it for a lot of smaller size problems. So let's get into building a machine learning model. So this is one of the problems that I thought was really simple. Just take a classic gender detection model where you have a female and a male. You think about, okay, what features, first of all, what data set would be good to represent male versus female? I looked at Vox Celeb. It's a 7,000 person speaker data set. There are 1 million utterances, 2,000 hours of validated audio. So it's a really big data set. So it can be used for a lot of problems. I thought gender would be a good one. So when I looked at this data set, I was like, okay, great, 7,000 speakers. Let's get one audio file from each of those speakers. Very simple. Make them into males, females, separated them, and then do some class balance. Balance males, females. So it'd be 2,312 males, 2,312 females, and then convert everything to a WAV file so we could do some featurization. So when I was thinking about this problem, I was thinking about that because there's a lot of things in here that you want to think about. Since Vox Lab is based on YouTube, it's correcting for things like noise, different microphones, ambient environment, some radio hosts. So a lot of the biases I was talking about earlier in choosing your data set, it's representative of a very wide range of things that would probably make this model work more robustly across different microphones. And so what I did right before this talk is I just open sourced this repository called voice gender detection and build a model with a lot of the techniques I mentioned. And so I can show you guys that really quickly. But before I do that, I want to show you this data set. So let me pull that up. So like I said here, I have all the female files in here that I mentioned. You can see 2,312 females, and I'll play a few here on my computer so you can hear it. And this is coming from...
Esta voz de alerta tan importante a las mujeres hispanas inician un viaje similar, un viaje al mismo lugar.
So different languages, right?
I'm saying someone else's words.
So it's not just one language.
So great.
Accents.
I love you. Não, por vaidade não. Todo mundo brinca muito com isso. Eu brinco.
This is male.
Reality, and that's what this show is proffered to do, and is, I think, achieved on so many levels.
Yeah, it would be very
Noise in the background. So this stuff to think about, right? I wanted to really hit home that point. Listen to your data. Make sure it's representative. And so if you don't have such diverse data set in the wild, it's really easy to overfit a model to like a really nice microphone in a quiet room, and it won't work in a noisy environment. And that happens. I can't tell you how many times I see people that I've trained do that and then think it works and put it in production, things fail. So please, like when you model, think about that. So I'll go back to the talk. So I set up this repo. You guys can probably follow the README if you want to build your own model. But when I was modeling this problem, and this is just my perspective, you guys can definitely model this in any way you want. I was thinking, oh, let's start out with MFCC coefficients, because there's a lot of other people that have solved this problem and done it, and I wanted to know what the standard accuracy was with MFCCs. And so when I looked at research papers and other repositories and other Kaggle and other, I guess, people who have done this problem with MFCCs as an embedding, typically you find the accuracy around 87, 88% with MFCCs. And so I was expecting that when I solved this problem. I ran the train audio classify scripts. So I'm going to go here and show you really fast. So I'm going to do two things really fast. So I'm going to take these files. I'm going to clone the repo and just do everything from start. Let's do that. So let's clone this repo. Let's go here. Yeah, all right. Out of this. I'll explain some other things in the repo for you, so you see why I did some things. So let's do it. Let's go to desktop. On it. Okay. Oh, I already had it typed out. All right. So we'll clone the repo. And then I'll take you through some of the way the repo is organized and what I just mentioned. So here we have already the data represented here in the form of features. It might take a while to load, but I do have, promise you, go voice gender detection. We'll go to CD data. And I'll go in here and just show you. Male, female. So we have here two arrays, one with males, one with females, and then if you look at you can see a lot of feature arrays here for the males, then a lot of them for the females. And so what I did here, and I'm going to take this out here really fast because you have to compress stuff from GitHub, is I took these two folders of files, which I have, I think, published online if you guys want the way I clean the data. Go ahead and did it, put it in the folder, and then I ran, if I get out of here, and I'm just going to run it because I already have all the dependencies installed. I ran the train audio classify .py script, and I'm intentionally not going over nor some of the warnings, some of the code, because I think some of the people in here aren't ML experts. But say you're trying to model two classes. Here it's males and females in this data folder. You have to put the folders in the data folder. You ask for the folder names. So here it'd be a males folder, females folder. You need to get the folder right with spelling. It then goes in there and featureizes all the files. So this would take a while, and then it ends up creating, like I had here, this file right here. So the idea is that with these featureizers, I'm going to stop this because it's going to take a bit. With these featureizers, you can easily featureize an embedding. In this case, I'll go over it really quickly. So you see like the code, and describe what it is. So here, it's featureizing all these MFCC coefficients using NumPy, as I mentioned a little earlier, as MFCCs. So the first 13 MFCCs, which are representative in the speech region, and all the MFCCs deltas. And these are often, like I said, used for automatic speech recognition. So it's a mean, standard deviation, min, and max. The reason why I use this feature embedding is that it's kind of independent of length. So a lot of these files didn't have necessarily, they had different lengths. So going back to the length correction problem, and taking the means, standard deviations, mins, and maxes of all the windows, you kind of have a length independent embedding. So that's one reason why I did that. And then here, what it does is it just goes through and looks for the files that you input and featureizes them. If it's M4A, it converts it to WAV, and then it goes in and creates just a feature. I guess here it'd be a JSON of each feature. So and then it creates that master males females.json. So it gives you an idea of what that was doing. I'm going to put those back into the workshop folder. And then when you want to train a model, this won't take too long actually. So audio classify. Once the file is there, you can actually just train it directly, which is why I had it in the repo. So do males, and it'll go through and actually build a model of each type directly within there. So you'll see here, there's a decision tree that's created 73% accurate. Gaussian naive Bayes classifier is 86% accurate. sklearn and a few others that will go through and actually optimize, actually just get the default model that I said before. So you end up doing that. I'm going to stop it because it's going to take a little bit. And then after that, you get a model file. In this case, it's a session that shows all the summary of the training. You can see here 33% were used for testing, and 2,311 were used for training, or 2,311 used in each class, and 33% were used for testing. And here's the sort of session summary. And you can see the hard voting, an ensemble method was the most accurate model out of all. So that was what it was used for the model. So if you want to make a prediction, I have in a script right here called load audio classify. So let's do that. Super simple. So here it will create a directory called the load directory. After you do that, you can put an audio file in there. Let's do one from here. Should be a lot of females. So let's just put like 8 females in there. See the predictions. So here, if you do the load audio classify script, it will go through, featureize all the files and make a prediction and output a JSON that is representative. So here you see the format of this is the file that was featureized was 0.wave. You can see that the prediction class is females. This was the model that was used, along with the model accuracy and the standard deviation of the model accuracy, and a few other things like the feature array. So very simple, just a gender detection model, and you can make quick model predictions. But you can imagine taking this idea and extending it to multi-class problems. What is the age of a person? Or you could take the voxelab and label each one in 20s, 30s, 40s, or adult, different ages. often celebrities had different ages throughout the recordings. So that might be interesting. You might want to look at, say, ethnicity and some demographics. There's actually a lot of work now being done on faces. So from an audio file, can you do a whole face of somebody, like their whole face, what it looks like, skin color, skin tone. So there's a lot of that kind of research going on that would be cool to do. All the depression work that we've been working on. But yeah, I took up exactly as much time as I wanted, about 1:42, but I'll open it up for questions for the rest of the time. Yeah, so any questions? Yes. Yeah, so I can go into some of that. I think that there isn't really a voice-specific deep learning library. I would say that Keras obviously is foundational. I really like Keras because it's interoperable with a lot of backend ML libraries like TensorFlow. You also can use pretty much any deep learning library. I think it's more in how do you embed the feature array more than the deep learning libraries. But the AutoML deep learning libraries, I would say Opal. Opal is one company that I would recommend looking into. Deep learning. Yeah, so yeah. Yes. I would. So we've done autoencoders, and there's like a lot of different autoencoder and configurations for audio. I think that in my opinion, it's still an emerging area of research, and I don't know. It depends on the problem. So it's hard for me to give a definition of the best. But I think that in my perspective, it's important to think of what's a speaker independent I vector, for example, that we would use that would correct for speaker variation as an embedding in that, and would the neural net overfit to the problem? I think sometimes that's a problem. So it really is dependent on data set and problem, but there are definitely good research studies out there for each problem in autoencoder. And we have one configuration we use that used one with like a Gaussian mixture model in the middle of the neural net, and it tended to correct well for those variabilities when you put like a GMM in the middle of, like, say, an autoencoder architecture. So that's a quick answer. Yeah. Oh, so yeah. So I'll put this up here for you guys to get the link. But I'll also post this in the talk afterwards. So if you guys want this whole presentation, I'm going to do a PDF of it. So if you guys, in this video, I'll try to get a recording and post it. But the repository name, sorry, I went through that fast, is voice gender detect, I believe. Just made it this morning. So voice gender detection. And I can make that really big. Yeah, I'll make that bigger. Any others? Yeah. They are, yeah. Yeah, I wanted to start not doing a deep learning model because I felt like the basics of data set often are more important. And just thinking about your data set, how you're curating it, how you're making it, all these biases. But in general, for example, the gender detection model that I have, with a few modified features in a neural net would be more like 99, 98% accurate. So just giving you like the difference. But I wanted to start out simple here because it was an intro talk. Yep.
Suppose they have more than one model to solve one problem. So, for example, silence detection. Like, whether the speaker is speaking, is the one model, or whether it has silence. Like, what are the strategies so we can combine?
So for silence detection, so when you think of that problem, I think, okay, well, there's a library called voice activity detection for Google, and you can actually clip silence with that library, and sometimes these VADs are better than building your model yourself. But in the case of silence detection, I think, okay, spectral power is probably the feature that you look at, because like, if you think of a microphone and somebody speaking, what feature are you like looking at that signifies a speech signal? So I often look at things like power, like variations, and usually 0.001 on the very threshold is like the one that leads to a voice activity detector. But when noise comes into effect, that works in a quiet room, but then you gotta think, okay, how do you detect speech in a noisy environment? So then you gotta think about, again, going back to the data set, what feature embedding you're using. It would work fine to put a 0.001 threshold machine learning detector on off of a threshold for a silence detector, but then in a noisy environment, it'd be thrown off completely because then the spectral power of a car goes up too. So then you gotta think, okay, what's deeper in the voice region? So it's good to think about, okay, well, add in MFCC coefficients and add in these engineered features that would be representative of the speech range, somehow clip the frequencies in the speech range, which is usually between 20 hertz and 20 kilohertz. So you can filter. So these are sort of the things you think about.
So my basic question is like,
Yeah.
if I have a different model which works to get that one work done.
Yep.
So how what are the strategies we can combine this kind of models to get a good prediction?
So if you had a deep learning model for a silence detect specifically, or just in general?
I have more than one model.
Yeah.
I want to combine those models to get the better prediction. What are the best strategies? Like what are the best ways to do that?
Well, you can ensemble both of the models together and make separate predictions and use that as and then add some layers as well on top of that to make a better, more robust model. But then it becomes bulkier and more expensive. So that's one way to do it. I've seen, like, for example, studies that have done that and achieved superior accuracy. Another way I think a lot about is just thinking about I think the feature embeddings themselves, if done the right way in a deep learning model, you could train one model that has better memory footprint. So when I think of our company, if we were to have 1,000 machine learning models at scale, I'm thinking about how do I create a better memory footprint, because there's a compromise between accuracy and footprint. So I think that it depends on what you're optimizing for. But I think ensembling in this case probably is the best. Just make two separate predictions, maybe have them ensemble into one over time, and another network would learn on top of that. But I don't know all the answers. I mean, I'm still learning every day. I mean, I started doing a lot of modeling like 2.5 years ago. I'm still learning, a lot of neural network architectures. I'm a huge fan of AutoML because I've seen it literally transform my accuracy in my models from being pretty good to like amazing, especially with DevOL and deep learning libraries. So I think that in the future, AutoML is the way to go. If you know the data set and how to curate it well, and you know these issues with the data sets, like number one cause of issue with this space is it works well in a small, restricted room, but it doesn't work out in the wild. I really want to iterate that, because you can get great accuracy, but where does it work? And I just think it's super important to think about. Does that answer your question? I'm trying my best to answer it. Any other questions, comments? Yeah.
So with features can also be used for
Yeah, definitely. So I think depends on how many words too. So I guess Google had a challenge of say 100. Yeah, so yeah, definitely. So that would be more of a wake word detection problem. So if you want to do wake word detection, I highly recommend looking at Porcupine. Porcupine library Python. It's an on-device wake word detector, and you can actually quickly train it with Porcupine. This is I created in the book a voice assistant called Nala, like from The Lion King, which is kind of cool. So here you can specify the wake word detector type somewhere in the settings. I think it's been a while since I've looked at this, so I'm gonna go back. But yeah, you can definitely specify this somewhere in the file. I'll have to look back at it. But yeah, so wake word detection, there are a lot of open source libraries out there. They use deep learning, and they're really good at detecting things. And there's like independent third parties who publish accuracies on such things. And Porcupine's good, but there's also some other, I think Pico Voice might be more accurate. I think that's the one I used in Nala as default. But yeah, it's definitely, check it out. Just I think look on these like repos. It's very clear. It's very easy to follow. I don't think it's that hard. But if I can help, I'd hack something with you. If you guys want to hack anything ever, just reach out to me. I'd love to like build stuff. So, any other questions out there? Yeah, sure. Yes, I'll post it right under the talk. There's like a section. I'm going to do that, and I'll post the video as well. I believe it's recording. Yeah, it's still recording. So I'll post both. Anybody else? Anyone want a book? There's a few books here. I'll grab. So I'll put them out first. I guess those two hands were the first three, 4 or 5. Okay. Well, I guess we can do. If everyone wants a book, I have to find a way to get you all ebook. If you don't get a book, just reach out to me. My email will be in the following. I'll try to get you an ebook of some form. So, yeah, come in. But yeah, I'll stop it. Please reach out to me after. I'll be around. Hopefully this was useful to you guys. So.